Welcome back. In this lesson we are going to understand what do we mean exactly by the ensemble learning. But first we need to import libraries as usual. So we'll import NumPy, we will import pandas, and we will import matplotlib just like before. And then we are going to import from sklearn a train test split, the label encoder, the metrics, the preprocessing, and most importantly the random forest classifier. This is the implementation of the random forest in sklearn. Okay, and then we are going to import also from taqaddum to have the progress bar and all this. And finally we are importing from decision tree my decision tree. So you might ask, what is this? We don't really have a library called decision tree. This is actually our own library right now. Okay, so what is a Python library? Python libraries are basically .py files, right? Or folders that contain .py files, right? .py is short for .python, so the extension of the text file is Python. Okay, so by this we know that this is a Python script, and this is different from .ipnp, right? So because here we have .ipnp, this is a notebook, right? It's short for intelligent or interactive Python notebook. Okay, so the notebooks are used for writing code and for writing documents just like this, so it's better for explanation and for educational purposes. But if you want to take only the code, then it's better to have the code in a .py file, in a script. Okay, and then you can reuse this script again. Okay, so what I have done here is that if you check here, you will see that we have decision_tree.py. If you open this, you will see that we have the function for the entropy, and then the function for the information gain, and then the function for the partition classes, the function for finding best split, and the function for finding the best feature, and most importantly the class we created, right? Our implementation for the decision tree, it's all here, right? So if you check, you will see that this code is 322 lines. Okay, so what I have done is that I went to the notebook, right, the decision tree notebook. In the last section, I took all the codes, all the functions that we have written in the last section, and I put them together in a .py file. Okay, and then I uploaded this file here, so we can import from the decision tree our class. We can import any of the features, so we can write from decision tree import find best feature. So by this we can use the find best feature function, and we can do this for the entropy, we can do this for all the functions inside this Python script. So by this we now have our own small library. Okay, so it will be very important because, as you will see, a random forest is basically a collection of decision trees. So when we want to implement the random forest, we will use our implementation of the decision tree, okay, instead of writing everything again. So this was very, very important. So this is our implementation from the last section, and I uploaded here adult data.csv, adult test.csv, and the decision tree.py. Okay, now we'll explore the data just like what we did in the previous section. We will have the columns names, we will read using the read CSV, we will use header equal none, and then the names for the columns are the columns names. And then we will drop the column which contains the state sample right in place. And here we are, we have this is the training data. After that, for the testing data, we will do exactly the same, but we will also drop the first row, because if you remember, the first row contained incorrect information, right? It was not really corresponding to an example. It was corresponding to 1 times 3 cross validator. So we wanted to drop this line. And after that, we want to convert also the age column, because this was a string in our test dataset. So we converted the age from a string to numeric, right? So using toNumeric function. So that's the training data, and this is the test data. After that, of course, we split our data into xtrain, ytrain, xtest, and ytest, and we use the label encoder and the fill transform inside the label encoder to convert this column from categorical to numerical. Okay, so this is basically what we have done in the last section. Now let's understand what is ensemble learning. Ensemble learning is basically combining many mediocre or weak models in a one super model. So if you want to explain what is ensemble learning in one sentence, this will be the sentence. Combine many mediocre or weak models in a one super model. So let's understand better by looking at an example. And this example is from this blog. I will leave it in the resources. So let's read the example together to understand better what is the ensemble learning. So let's say I want to invest in some company, but I'm not sure about its performance. So I look for advice on whether the stock price will increase more than 6% per annum or not. Okay, so this is the question I'm asking. So I decided to approach various experts having diverse domain experience. So not only experts from the same domain, no, they are from different domains, but all of them are experts in their field. So I will first ask an employee of the company, okay, the company that I want to invest in, and I know that this employee is good at knowing the internal functionality of the company, and he also has the insider information about the functionality of the firm. But he lacks a broader perspective on how our competitors innovating. So he's only working in this company and he doesn't really know what other people or other companies are doing. Okay, and he also lacks on how is the technology evolving and what will be the impact of this evolution on the company's product. Right? So he is good at some stuff and he is bad at other stuff. So the accuracy of this employee, in the past he has been right 70% of the time. So 70% of the times he was correct and 30% of the time he was not correct. Okay, then I will ask a financial advisor of the company. So he's also someone who is working in the company, but he is a financial advisor and not a regular employee. So he has a broader perspective on how companies' strategies will fail in this competing environment, but he is bad at other stuff, right? And his accuracy is 75%. And then we ask a stock market trader. So he is good at other stuff and he is bad at also other stuff, right? So for each person or for each expert, he is good for some stuff and he is bad at other stuff. Okay, and we have the accuracy for each of them. So here we have 70%, 75%, and the stock market trader is 70%. Then we have an employee, but for the competitor company, right? So he was 60% accurate all the time. And then we will ask a market research team in the same segment, and this market research team was correct 75%. And then finally we will ask a social media expert, and this social media expert was right 65%. And you can look at this example and read all the details about all these people, what they are good at and what they are bad at. Okay, and it makes really so much sense. Now, what is the accuracy of the 6 experts combined? The accuracy of the 6 experts combined is 1 minus the multiplication of the error of each expert, right? So if we have the first expert was incorrect 30% of the time, we multiply this 30% by the 25% for the second expert, by the 30% for the third expert, and so on. So if they were all correct, right, then we will have an accuracy of 100%. So this is the equation for getting the accuracy of the 6 experts combined. So as you can see, even though each of them was accurate 65% to 75% of the time, if we combine the accuracy of all of them, then we will get, using this equation, 99.92% accuracy. So this is a little bit suspicious, right? So this doesn't really make sense. So what is the problem in this approach? The problem is that we assume that all the predictions, right, this prediction and this prediction and this prediction, are completely independent on each other, right? We said that each of them is an expert in his field and they all have different fields, but this does not mean that there is not some kind of overlap between these people, right? Because using this equation, we assume that all of them are completely independent on each other. And this doesn't really make any sense and it's not realistic at all. Okay, so this equation is not correct. So how to solve this problem? In order to solve this problem, we follow one of two approaches. We either use bagging, okay? So bagging is basically parallel training of different models using overlapping training sets, okay? So bagging, we train different models, not only one model, but different models. And these models are trained in parallel. So the first model doesn't really know what is the accuracy of the second model or the accuracy of the third model, and so on. And the training dataset that we use is an overlapping dataset. So we can have 80% or 70% overlap between the first model and the second model, another 40% overlap between the second model and the third model, and so on. Okay, so this is the idea of bagging. And bagging is short for bootstrap aggregation, right? So B is short for bootstrap and ag is short for aggregation. Okay, we will understand everything about bootstrapping and bootstrapping aggregation in the next lesson. And the second way to solve this problem is by using boosting. Okay, boosting is sequential training. So bagging is parallel training, boosting is sequential training. Sequential training by iteratively reweighting the training examples. So how we can reweight the training examples? We reweight them such that each model focuses on a different subset of hard examples, right? Because all the models, let's say in this example here, 65% and 75% and 60% and so on, right? All of these people are actually incorrect for some examples or for some years, right? So we want to focus on these years and make the machine learning model focus on them, right? We don't really want to focus on the examples or the years that all the models are actually good at predicting, right? So we don't really want to focus on this 60% overlap between all the models or all the experts. We want to focus on the part where they all wrong. Okay, so this is the idea of boosting. Okay, this is the idea of boosting. Now we understand what do we mean exactly by ensemble learning, and we saw a very naive example, and we saw that using this equation or using the idea of just combining them as they are is very wrong. So we need to find a way, and we have two ways to solve this problem. First we have the bagging, and then we have the boosting. In the next lesson we will start understanding what do we mean exactly by bagging, bootstrap sampling, and so on. Okay, so let's go to the next lesson.